Okay, now let's use the Laurel expansion to classify the isolated singularity. So that's a corollary 1.18. Okay, 1.18 corollary. So let z equal to a be an isolated singularity. Singularity of f, and let f of z be the doubly infinite series from negative infinity to positive infinity, a sub n z minus a to nth power be its Laurel expansion. In this punctured disk, the analysis ANN centered at A with inner radius 0 and outer radius R. Okay, and then we have the following classification. Case 1, z equal to A is a removable singularity if and only if a sub n is equal to 0 for n less than or equal to -1. So basically, if there's no negative part, negative exponent part, then that's a removable singularity. And 2, z equal to a is a pole of order m if and only if a negative m is not equal to 0. So be careful, m is always non-negative. Okay, m is always non-negative. So negative m is a negative exponent, negative term. And a sub n is equal to 0 for all n less than or equal to negative m plus 1. You cut it here, and from negative m, after negative m, the left part will be always 0, a sub n. And 3, z equal to a is an essential singularity if and only if a n is not equal to 0 for infinitely many negative integers. And negative integers. And so basically, it's a real doubly infinite series. And the first case, the removable singularity, it means that you symmetrically cut at 0 all the negative part. Well, for the when I say negative part, means the negative indices. All the negative indices are 0. And second part, it means we will really cut it. It's just the series is just infinite in the positive indices, and negative indices, it contains some term, but eventually it will be after those finitely many negative indices, other terms are 0. Essential singularities just means it is really a doubly infinite series. It is infinite in the negative indices part. It is also infinite in the positive indices part. All right, so that's a difference among those three cases. The proof is It's not hard. So for the case 1, if an is equal to 0 for n less than or equal to negative 1, then we define g of z is just a sigma n from 0 to infinity, a sub n z minus a to nth power, and g of z is analytic, right? Power series, convergent power series is analytic function, and the g of z and f of z coincide in this annulus centered at A with the inner outer radius 0 and r. Right? Then this is A is removable. A is a removable singularity. All right, this is one direction. The other direction is obvious. If it is a removable singularity, then you will have a sub n equal to 0 for n less than or equal to negative 1. That's for sure. We actually had that discussion before. And second, if a n is equal to 0 for n less than or equal to negative m plus 1, okay, you cut it at n equal to negative m, then what we can say? We can say z minus a to mth power times f of z has a removable singularity. Right? So in this case, it's because f of z becomes a negative m z minus a to m's power. Remember, when n is less than or equal to this term, the coefficients are always 0, so you don't copy them. So you have a negative m minus 1 z minus a to power m minus 1 and da da da. Right? You start from negative m, and then you multiply it by z minus a to mth power. You will have a negative m plus a negative m minus 1 times z minus a, and da da da, and this becomes a power series. A power series is analytic, so it's z minus a is a removable singularity. Correct? Okay, z minus a has a removable singularity, and this is a definition. A is a pole of order m of f of z. Oh, be careful. We assume this a sub negative m is non-zero, so it's definitely a pole of order m. Okay. And the other direction was discussed, and also it was a property when we right after the introduce the pole. Okay, and case 3, f has an essential singularity. At z equal to a, if and only if z equal to a is not removable, not a pole, right? That's a definition. What is essential? Essential just means it's not removable, it's not a pole. You exclude the first case, exclude the second case. So the case 3 is the case 3 is a corollary of 1 and 2. So it has to be infinite. You cannot stop at any negative index. the negative power series can never stop at a negative at any negative index. So that's why it is really contains a really infinitely many negative integers, so that a sub n is non-zero. So that's why once you can classify case 1, case 2, then case 3 will be automatically correct. Right? So that's the proof of a corollary 1.18. The proof of a corollary 1.18. In the exercise part, there is a sequence of exercise 7, 8, and 9. 7, 8, and 9. They give you a way to identify or classify isolated singularity by examining this one, this limit, z minus a modulus to s power times modulus of f of z is equal to 0 or infinity. So for some real number s. So you are going to check if you're interested, see how to work out this exercise 7, 8, and 9. You work in order because one depends on the previous one. All right, so that's it's not too bad. It's not too bad. All right, so now let's see what is essential singularity. Essential singularity means when you let z approach a, the modulus of f of z does not exist. The modulus of f of z does not exist. Here it means does not exist means it's not even approach infinity. Remember, if it exists, it will be removable. If it is approaches infinity, it's a pole. Well, the other case means it does not exist. So it can be whatever way. Sometimes here, sometimes there. All right? So in the next part, in the next theorem, we're going to show that actually f of z will be close to can be close, not will be, can be close to any number in C when Z becomes close. To A. So when Z approaches A, this f of Z really go here, there, here, there. It can be very, very close to any other numbers. Any or all the numbers can be close to all the numbers. So that's a theorem 1.21. Actually, even stronger, the Cos theorem says even stronger. Cos theorem says the f of z for z in a neighborhood, some neighborhood, I don't know the radius, let's just put whatever radius, small enough, f of z will just miss at most 1.11, not open, 1 point in C. It will only miss at most 1 point. Sometimes it does not miss any point, but if it miss, it will miss at only 1 point. Of course, it will reach almost all the points except one, possibly one. And here just say close to it. So this one, the Cos theorem is stronger than the theorem we are going to prove. But we don't prove this Cos theorem in our class now. Okay, now let's see what we are going to prove. Causality Weierstrass theorem. Okay, Causality Weierstrass theorem. If f has an essential singularity at z equal to a, then for every delta greater than 0, well, you should have a sufficiently small delta, because if delta is too big, it may not be inside the domain of f. But whatever, we just keep in mind the delta will be small. Then you see the image of the annulus A puncture point center and with outer radius delta. This is image, and we take the closure, it's C. Close to them, so when we take the closure, it will be everything. Okay, so let's see the proof. Well, F is analytic in the annulus, the punctured disk in this annulus. We're going to show the closure is C. It means we need to show that for any C and C in C, any complex number, any epsilon greater than 0, how close? And we need it for arbitrarily small disk, and for any delta greater than 0. All right. So C epsilon is used to measure how close this image f of C, not f of Z. Yes. F of Z will close to this C, how close. And the delta means this Z can be selected how close to A. Okay, so we can find a point Z in this annulus, not annulus, such that the f of Z minus this C is less than epsilon. All right, f of Z minus C is less than close enough to epsilon, close enough to C with radius epsilon. All right, so now we're going to prove by contradiction. Assume false. If we assume false, we're going to exchange all the for all to be there exist. There exist means for all, and this condition is incorrect. All right, so here it means for all C, so there is a C in C, all epsilon, and there is an epsilon greater than 0. And all delta, it means there is a delta greater than 0, such that we can find one means for all Z in annulus, we have f of Z minus C incorrect greater than or equal to epsilon. Right? So whenever you want to get the converse statement, you're going to prove by contradiction. You need to change all the for all to be there exist, change it for they exist to be for all, right? Okay, now let's check it. Let's get a contradiction from the our assumption. So f of z minus c is going to be greater than or equal to epsilon for every z from this analysis. Then what do we get? We get z minus a to the power -1 in the reciprocal part, f z minus c. This limit z approaches a, the difference becomes smaller and smaller, and take the reciprocal, it becomes bigger. And this one is greater than epsilon. Epsilon times infinity is infinity, right? Epsilon times infinity is infinity. Why is it indeterminate? Be careful here. This is actually, you see, this is just f of z minus c over z minus a. It is determinate. It's not indeterminate. It's determinate because the numerator does not approach 0. Numerator is greater than 0. We're talking about positive. Denominator approaches 0. And positive number over positive 0 is always positive infinity. It's not indeterminate form. Indeterminate form both approaches 0. Right? Okay, so we have certain limit is infinity. Then what we can say? We say A is a pole. So the function z minus a to power -1 f z minus c has a pole at z equal to a. Has a pole at z equal to a, right? Pole means when you let z approach this singularity, you will get infinity. The modulus will be infinity. Okay, so let m be the order of the pole. M is order of the pole. Then what does it mean? M is order of the pole. It means z minus a to mth power times z minus a to -1 f of z minus c. This has a removable singularity. Right? Whenever you have a pole, it just means you multiply it by the proper power, you will have a removable singularity. Removable singularity does not mean the evaluation is 0. If you want it to be 0, you have to multiply it by additional z minus a. Okay, so this is means it is analytic times z minus a. The evaluation is 0. The evaluation becomes 0. So what we get? We actually have, you cancel this, we actually have the limit z minus a, z approaches it, z minus a to mth power f z minus c is going to be 0. It's not necessary to have m plus 1's power. Just m's power is enough. But of course, you put additional power, higher power, you automatically have 0, right? So in the book, they use the limit z minus a and z approaches it, z minus a to power m plus 1, f z minus c modulus is 0. That's correct. We don't say it's incorrect, but we just say it's not necessary to put m plus 1. M is enough. Well, it doesn't matter. Let's check the limit z approaches a, not minus, z approaches a, z minus a to power m plus 1 f of z modulus f of z. Let's not talk about limit first. And we're going to use triangle inequality. It's going to be less than or equal to z minus a to power m plus 1. Here f f z minus c plus z minus a to power m plus 1 modulus of c. C is still the same c. We just insert minus c plus c, and we got this triangle. And of course, this side is greater than or equal to 0. And then we apply the limit. We get the squeeze theorem. Z approaches a modulus a z minus a m plus 1 f of z less than or equal to this term. We check it. The limit is 0. This term, c is constant. When z approaches a, this is continuous function is 0. So we get the limit z minus a, z approaches a, z minus a to power m plus 1 f of z is 0. What does it mean? If this one is 0, it means you have fz times z minus a to power m has a removable singularity. It will have a removable singularity. Right? Remember, this one is equal to 0. Be careful here. This one is equal to 0. It implies z approaches a, z minus a to power m plus 1 f of z is equal to 0. This is the only case when we can have a implication from modulus to the original function. Be careful. You can only have this equivalent statement when this place is 0. If it's any other non-zero complex number, this conclusion is incorrect. All right, and this one is 0. We had a characterization to say that if such statement is correct, z minus a times g of z is equal to 0, then this one has a removable singularity at a. So that's why we get this one. Well, f of z minus z, f of z times z minus a to m's power has a removable singularity, then what it tells us? Well, it means z equal to a is a pole. Right? Z equal to a is a pole, but z equal to a is an essential. Is an essential singularity. That's a contradiction. The contradiction comes from our statement. We say that we assume that it is a false, right? We assume it's a false, so that's why we have such contradiction. All right. Okay, so by this contradiction, we showed the Casorati-Weierstrass theorem. It says the closure of the image of f of analysis is a whole complex plane. Okay. Okay, so in the exercise part, it's better for you to do that exercise 7, 8, and 9. You will understand better about this classification of isolated singularity. Of course, other functions, other problems are also good, but if you have time, you can check them. If you don't have time, just leave them there. All right, so let's check next. Next section is about the residues. The residues. What is the residues? The residue comes from the following computation. If we have an analytic function and we have a homologous to 0 curve, then this integral is always 0 by the Cauchy theorem. F is analytic. And gamma is homologous to 0, then this is always correct. The thing is that what will happen if F has a singularity at A? What is this integral? What is the value of this integral? When we say singularity, A could be removable. If A is removable, f of z is still considered as an analytic function, so this integral is still 0. So in principle, essentially we are interested in the case when A is a pole or essential. If A is a pole or essential singularity, what is the value of this integral of f along the gamma, homologous to 0 gamma? All right, so that's what the idea of the residue. Let's see the definition first. So let F have an isolated singularity at z equal to A. And let f of z has doubly infinite Laurel expansion, n from negative infinity to positive infinity, a sub nz minus a to nth power, be its Laurel expansion about z equal to A. Okay, then what is the residue? The residue of f at z equal to A is the coefficient a sub negative 1, a sub negative 1. So residue is a number, it's the coefficient a sub negative 1. So we denote it by residue of f with respect to A is equal to a sub negative 1. Okay. Okay, so what is the usage? What is the usage of this residue? The usage of the residue is in the answers of this integral. That's the next theorem. It's called the Residues theorem. The Residues theorem says let f be analytic in the region G except for the isolated singularities a sub 1, a sub 2, and a sub n. We only consider finitely many isolated singularity. If gamma is a closed rectifiable curve in G which does not pass through any of the points AK. And if gamma is homologous to 0, in G, or check back what the homologous means. The Wanting number with respect to the exterior point is always 0. Okay? Then what we can say is that 1 over 2 pi I integral along gamma f, the integral of this analytic function with poles, all right? It is equal to the sigma k from 1 to n, the Wanting number of gamma with respect to AK times the residue of f with respect to AK, case from 1 to n. Alright, so this is a usage of the residue. Of course, we also use the Wanting number. Alright, so well, let's see how do we prove it. The proof is not difficult. The proof is very constructive. The proof becomes very, very constructive. Let's see how we get it. Well, we don't want to always copy the Wanting number of gamma with respect to AK, so we're going to give it a name. Let mk be the Wanting number of gamma with respect to AK. That's mk, k between 1 and m. N, not m, n, 1 n. There are n Wanting numbers, n singularities. And you see, this is G. This is A1, A2. Let's just draw A1, A2. And this is gamma. It is gamma. We are going to draw a disk for each point so that this disk is totally contained in G and it does not intersect the gamma. And this is radius R1, this is radius R2 and Rn, right? So choose positive numbers R1 up to Rn such that no two disks B, AK, RK intersect. So they are really isolated. None of them intersects gamma. All right, and each disk is contained in G. So you cannot draw a huge disk. Of course, if it's a huge disk, it will not intersect the gamma, but it's not inside G, so it's not allowed. We just assume it's very tiny, very, very tiny. All right. So for this, each circle, we define gamma k. We have circle. Circle have gamma k. Gamma k is AK plus RK exponential of what? Exponential of 2 pi it, right? 2 pi. If you have 2 pi it, you get the counterclockwise orientation 1 round. And this time, we are going to get negative 2 pi I mkt. You will have mk round and with the opposite orientation. If m is a positive number, it's going to be negative means it's clockwise orientation. So m is a positive means the original gamma has a positive positive Wanting number. Then this gamma will give you the negative Wanting number. Those gamma k are used to cancel the Wanting number property behavior for t between 0 and 1, between 0 and 1. Right? Okay, then what we get? Then we get, be careful here. If you have this gamma 2, the Wanting number of gamma 2 with respect to A1 is always 0 because they're so totally separated. So for j between 1 and gamma, n, not m, it's not m, it's n. There are n singularities. There are n singularity. We get the Wanting number of gamma with respect to aj plus the Wanting number of gamma k with respect to aj. K is from 1 to n, is always 0. So this, for this gamma 2, the Wanting number with respect to a1 is 0. Others are 0. But for gamma, the Wanting number is mk. But gamma 1 Wanting number is negative mk. So again, this gamma k is used to cancel the Wanting number at this aj. At this aj. All right. So what we get? So the gamma is homologous to 0. Not so. Sorry. We know that the gamma is homologous to 0. It means the Wanting number of gamma with respect to W is always 0 for all W inside C but without G. But in this case, the W cannot be AJ. A1 up to AN are supposed to be inside the G. But here we also show that the sum Wanting number is 0. And be careful here. The Wanting number of gamma k with respect to W is also equal to 0. This is a contractible circle, and W is outside. So this one is equal to 0 for all k between 1 and n and W inside outside the G. Right? So by these two conditions, we can say that the Wanting number of gamma with respect to A plus sigma k from 1 to n, the Wanting number of gamma k with respect to A is always 0 for what? For all A not inside the G and not for A not inside the G and also possible A1 up to AN. All right. So for we just want to add A1 AN to this collection, of 0 Wanting number. So that's what they say for all. Okay, in the textbook they say the following: for all A not in G minus A1 A sub n. So they just want to add those singularities to this W selection. Okay. Remember, F is not analytic in G. you have exceptions. But this time we remove this A1 up to AN. So F is analytic in what? In G without A sub N. This is okay. You remove the singularity, F is analytic. And this gamma union gamma 1 union gamma k, this is homologous to 0, right? In this region, in G minus A1 AN. So by the Cauchy theorem, we have the integral of f along gamma plus sigma k from 1 to n integral f along gamma k. This integral is 0. This is 0. Okay, now let's try to compute it. Try to compute this integral. So f of z is the doubly infinite Laurel expansion. It is at AK. At AK we have this doubly infinite Laurel expansion. And it's the series, it is uniformly convergent. On this closed disk BAK RK. Alright, so what we have? We have the integral of f along gamma k is term by term integration. And from negative infinity to positive infinity. And we know if this is if a gamma is if n is a positive, n greater than or equal to 0, this integral is 0. It's analytic. N is strictly less than 1. The integral is what? The integral is also 0 because z minus ak nth power has antiderivative, has a primitive. Okay, but when n is equal to negative 1, it's a 2 pi I and mk. Gamma, you have a 1 in number. Negative. Alright, so that's why after the computation, it is equal to it should be negative 2 pi I mk. Oh yeah, times b negative 1. B negative 1. Correct. This integral is a negative 2 pi I m and times b negative 1 because there's a negative 1 here. This classification is just about this integral. All right. So for each one you have such Laurel expansion. Here, check here, you have several ones. So for each one you have a Laurel series expansion, and for each Laurel series expansion you have the one in residue. So this is a negative 2 pi I mk, the residue of f with respect to ak. And you add them together. Be careful, here the negative sign. There is a negative sign because in our computation it's a negative 2 pi I mkt. It's not a positive. It's not a positive, it's negative. It's negative. In the book, they write 2 pi I, the Wanning number of gamma k with respect to ak, residue fak. That's correct because the Wanning number of gamma k ak is negative mk. It's negative mk. Okay, then you add them together. With this negative sign, you're going to move to the other side. So f integral f along gamma is equal to, okay, so sigma k from 1 to n 2 pi I mk residue f ak. 2 pi I, you move forward, divide by 2 pi I, and you will get the formula. This is a winding number of gamma with respect to ak, residue of f with respect to ak. So that is the computation. All right, so we just tried to balance the winding number. We want to remove the singularity from the region G. Without that, we cannot apply the Cauchy theorem, because Cauchy theorem requires f to be analytic in it. But f is not analytic in G, it's analytic in this set, the G without A1 up to A. Okay, so with the help of the residue, we can write down the value of analytic function with singularity along the homologous to 0 curve. Okay, so we will continue this discussion in the next video. Thank you.